Okay, let's start over again. So we saw last week, we saw our first red-black trees, our first self-balancing trees. And why did we need these self-balancing trees? Why would we actually, like, assuming we want a binary search tree, right? So why do we want self-balancing? Because what was the problem? Remember, I'll open up my paint. Well, what is the problem? What's the problem is binary. Okay. No, you were here, guys. You guys were here. You just don't remember. Okay?
I was sick.
All right. Binary. Let's go back to a regular binary search tree, right? Visualization, right? And what was the problem? Why we need this in general? You know this, right? You guys know this. Just it seems maybe too obvious, right? But this is binary search. This has no balance, right? If I do this, right? If I do this, right? This is the problem.
It can be a linked list.
It basically degrades. We get the worst case performance of this. We don't want to have a linked list performance in a binary search tree because this is a valid binary search tree. It's just a bad binary search tree. This is what we want to avoid, right? That's what we want to avoid, right? But that's why, basically, I would say, in in 60s, AVL trees were the first self-balanced data structure invented. If I remember correctly, the inventors were in Soviet Union, I believe, AVL trees, and they were in Moscow, I believe, right here, Velsky, Adelson, right, yeah, Adelson, Velsky, no, two guys, sorry, Landis, right, and Adelson, Velsky, right, that is 1962, right, pretty amazing for that year, right, so, right, basically the first binary search tree structure which is self-balanced. Afterwards, there are many other ones, like red-black tree, I think somewhat unjustly is more popular. AVL trees have actually better, I would say in some cases, better performance. Again, it's not completely even, right? There's always some trade-offs, right? For some applications, red-black trees are better. For some applications, AVL trees are better, right? But the idea again is to avoid this, to force your tree to rebalance, right? So basically, the big idea is that in AVL you are not allowed to go as far out of balance as in red-black trees. You have sort of like a balance factor, 0, 1, and -1. Let me show you a visualization first. I'll start with the actual real AVL tree in action, and then we can see if we can figure out what it does actually, like a reverse engineering. Let's reverse engineer AVL tree, right? Let's see if we can figure out what it does, and then we'll go to some theory which is relatively well, not painful, but of course what it will involve. What's the hard part about these self-balancing structures is the rotation, of course, right? It's kind of painful sometimes to figure out. But let's take it's AVL tree. So I'll insert 1, right? 1. So far so good, right? 1, right? 2. Okay, right? Push back, okay. Now let's do 3. Okay. There you go, right? So it forced this. Okay, so what happens if I insert, let's insert 5, right? It'll go here, right? Well, will it rebalance? No, because it shouldn't rebalance. Why? Because there's nothing to rebalance. I mean, again, so you can see 3, 1, 2, 3. Excuse me?
It's all 0. Rebalance.
Oh, yeah, because you can't really rebalance better, right? I mean, this is already good, right? So, yeah. So if I insert 0 here, what's going to happen? Nothing, right? If I insert 0, it shouldn't rebalance, right? Okay, right. So obviously if I insert 0.5 or, well, I guess I can insert 1 here, right? Let's insert 1. It should go here. No, yeah, it's fine, right? And of course you can insert, 2 here, I guess, or something that maybe a little bit hard to see. Okay, so how about 6 here, right? So let's see. That's a good question. Is it going to be allowed to have 6? If I insert, like, I'll insert 7, right? It goes here. we know how to rebalance it, right? 5 will go here, 3 will go below, right? And 7 here, right? That will be the rebalancing. The question is, I don't think it will force at the moment. I think it will be next time. Yeah, no, immediately actually. So actually better performance. So pretty good actually, right? So you can see how it is much more strict. The red black trees, you get out much more higher out of balance. So obviously here, right? So I'll do 11, and again, if I do 11, it can be rebalanced by 9 being rotated here and 7 go down, right? Yep, rotation, easy, right? And so on and so on. Obviously, it's not just single rotation. There's like I think 6 types or 4 types, right? That makes it complicated. The basic idea I think is apparent, right? You have some balance factor, right? So now the number, this number is here. Okay, yeah, okay, got you now. So what does this say? Okay, this number 4 here, right? This is the extra information that AVL3 keeps. Red black trees only had a big one bit, red or black, right? Here you have a depth basically, right? So 4, and this is 2. What does it mean? Well, here you have 3, right? 2, 1. So this is 1, 2, 3, 4. 1, 2, 3, 4. So longest pass, right? 1, 2, 3, 4, right? Here, what's the longest pass? 1, 2, 1, 2, right? Here 3, 1, and 1, 2, 3, 1, 2, 3. So what the thing is, it cannot get out of balance by more than 1, basically, on the same level, basically. I think that was the thing, right? So 2 and 3 is okay, but it cannot go out of balance by more than 1, basically, right? So if I start adding something too much, right, it will go out of balance, basically. So if I add 1 here, let's see, let's add 13. Friday the 13th? No, Monday the 13th. No, 26. Okay, so 13, right? Yep, look, see? So this is a complicated, right? Complicated case. We'll look in the slides in a moment, right? But you see again, it keeps this balance. It's not perfect, right? But it's very close to the optimal balance, basically, right? So not full, not complete, not perfect binary tree, but still close. So it cannot go. It's much tighter range basically than red black tree basically. Okay, well let's look at some theory. Now you have the basic idea. And if I can remember the basic theory, visualization. And I believe it's University of Washington. I believe has. And then we'll see if we can implement ourselves in the second part of lecture. Hopefully, not going to be easy, right? Yeah, it's the University of Washington, right? So basically the balance is left side and right side, right? So 0, right, difference. Again, let's look at this here, right? So here you don't have a left side and right side. You have 4 and that's it, right? But here, 2 and 3, right? So difference is 1, you know. So one side could be by 1 more than the other side. And that's all. 2 is not allowed, right? You cannot have 4 here, or you cannot have 1 here, basically, right? If these were not existent, that would not be a valid AVL3, right? So only can be off by 1 in one direction, left or right side, basically. Very close to perfect balance, basically, right? So this is, well, obviously it says AVL3, right? It does match this, right? So again, here, 1, 1, even, perfect, 0, right? Here, 2 and 2, that's fine. So now, if I add, let's see, can we make it somewhat, can I add something here? Let's take a look. Let's add 8. What will happen? This will be 3. This will be 4. And that's a problem. You see the problem? If I add here something, right? There's no problem here, right? It will be 2. This is 1. This will be 3 and 2. Not a problem. The problem will be here. 2 and 4, right? This will gain. I'll do slowly. I'll do add 8. Insert. 9, less, 5, more, 7, more than 7, 8. There we go. Now we need to start calculating these heights. Obviously, it's not a free operation, right? It doesn't cost you. It costs something. Right here. 2, right? And we are fine. 1 and 2, no big deal, right? Here, 3. 3 and 2, you know, check the children, right? 3 and 2 is fine. Here we have a problem. 2 and 4, that's a problem. Because difference is 2. And 2 is not allowed. 2 is not allowed. And this means what? I'm trying to see what's going to happen. Okay, let's see if I can remember myself. How could we rebalance? Well, it will involve what's the idea? We need to move, this 2 has to go left side, right? And this should go up, I believe. But let's see what's going to move up. If you move 9 here, well, and I think this 5 will attach to this here. Yeah. Yep. So 9 will go up, 2 will go down, right here, and 5 will be a child of number 2, I believe. I might be wrong, but let's take a look. Right, 5, yeah, 1, 2, 3, 4, 5. Okay, this needs to be fixed. Well, 5 itself is not a problem, but 2 and 4 is a problem. Double rotate left. So, first rotation, wow. Maybe I was wrong actually. Different type of rotation. Wait, let's go back. I did it wrong. Okay, so 5 moves up. Yeah, 5 moves up. And then, 5 moves up. And 2 is less. But well, let's see again. 5 moves up. This is harder than I thought actually. So 5 moves up, right? This is 9. But this 3, this 3 was part of 5, and now it's attached to 2. Okay, this is harder, right? Yeah. So this is much more involved operation, right? It's like double rotation, right? So again, in 1962, they spent a lot of time thinking about this and came up with this, right? So this is probably the most involved operation, right? And now we are like almost perfect. Again, not perfect. Why not perfect? Because of course here, right? To be perfect, we have to, well, to be complete, right? We have to add them here, basically, right? But this is already very good, right? You can agree that this is a good-looking tree, right? So again, so at the cost of expensive, more involved rotations, right? And what's the other cost? What's the other downside? Well, in old days, do we?
Tracking the layer.
Yeah, and basically again, as far as space, we need to store a number, not just a bit, right? These days we don't really, hey, we have, we can spare, right? We can spare a character, we can spare an integer, right? No problem. But old days, they were, okay, that's why I think it didn't take off, because you had to store an, number.
But technically, well, I've heard of this method that you could replace two numbers using XOR.
Yes, there is trick. So there's some tricks. So we can still save some memory actually. Yeah. So there's various tricks to optimize this, right? But yeah. So these days AVL trees, I think people are coming. Lots of paper research. This actually AVL trees should be, many libraries should be using really AVL trees instead of red-black trees, right? So you'll see there is some case where AVL tree is better than red-black tree. Well, first of all, anytime you have to do lookups, right? It will be slightly faster. Still log n, both are log n, but slightly better constant, right? So because it's more balanced, right? If you have if you're doing a lot of lookups, which is what we usually do, right? AVL tree will be better. If you do a lot of insertions and deletions, right? Then red-black tree is probably going to be faster because it's a faster operation, less rotations, less work to do this, right? So AVL trees involve more frequent rebalancing, right? To keep up this balance, basically, which makes sense. So idea is actually maybe you could start when you're doing your insertions, use red-black tree, and maybe at end, okay, you have almost finished your data structure. Transfer it to an AVL tree and do these final rotations at the end. That's possible, right? Yeah. But okay. Now, so hopefully you have a basic idea, right? To balance. So yeah, it turns out you can calculate 1.44 log n. That's the worst case rebalance, right? Misbalance, right? So, right here, right? So, something like this. So -1, basically balance, right? So this is a normal binary search tree, right? 8, 11, right? Yeah. So 3, right? 1, 2 is fine, right? So these children don't have, well, in this presentation is using different way of counting, right? They're using height, right? So 1, 2, 3 hops, not nodes, right? 1, 2, 3 hops. Here, this is what makes complicated, right? This is not using, it's using 1, 2, 3, 4. Different way of counting, but same result, basically, right? I mean, we will get the same, off by 1, right? Not an error, but basically different way of approaching this, but it's leads to the same way of results, basically. Here, we assume that no leaves, these are leaves, 1, 2, 3, 4, 5 leaves, right? Leaves are the ones that don't have any children, right? So they have, they assume height is 0, but here we count in this visualization, we count them as 1. But okay.
I have a question.
Yeah.
Can I construct a regular binary tree and then apply this AVL tree algorithm to turn it into AVL tree?
Yeah, well that's exactly what I was thinking. It should be doable, right? To do it at n, right? Basically, right? But the thing is, okay, you do a binary search tree, you have you can do it, but this means basically you have to figure out where you're going to pick the numbers, right? Because you have some sort of tree structure, but let's imagine if you have this, right? So there's no button, turn it to AVL tree. So how could you do it? Well, easy. You just take, maybe start at the beginning, right? And start.
Firstly, you would have to look through to set the index.
Yeah. So basically, I mean, the easy approach that you have is kind of generic binary search tree. You just take numbers from anywhere and start making a, have like next to it, right? You have next to it and start building AVL tree, right? It'll work, right? So only question might be interesting research question. Where should you start, right? If you have generic binary search tree, you don't know how good it is, right? How could you figure out a good starting point? Because you want to minimize this number of rotations, right? You want to minimize your work, right? So here, right, you probably do it 3, right? You move this up, right? And then these will go down, right? Something like this, right? So be interesting, right? So let's see actually what happens with if I do this AVL3, right? I'll clear it, right? Let's pause it. Oh, no. Okay, here you go. So I'll do this 1. This will I'll play 2, right? And we already know right here 3, right? On 4. This is allowed, right? And we know 5 is going to be insert. And like this, right? This is AVL3. Very good. So we had 2 rotations, right? We had 2 rotations. Here, movement. You have to look up Google Scholar or something, see if there's any research. How is there any tricks you can do? Because this is the obvious approach, right? You just take, you have binary search, you just keep, start building up AVL tree basically from it. It'd be nice if you could somehow sort of like do it in place, maybe use the existing structure and some sort of like save some time, some memory. Maybe you can use something from the existing tree. The thing is, how do you extract the structure? Because you don't know. Is it linked list? Is it really bad? Well, you could calculate depth, right?
Well, you could start with the breadth first.
Yeah.
And kind of go through all of the nodes and set those layer indexes. And then do those transfer.
Yes. Yeah, so I think there is some room for actually transference, right? See, so you can maybe, start with generic. Oh, it's binary search. Maybe you can do some operations to build up, actually make it sure it's AVL tree, right? So let's look at what's not an AVL tree, right? So this is so why is it not AVL tree? Because 0, 2. Everything else is fine, right? 0, 2, right? Yeah, so, but here, right, now the thing is here might be not obvious. Why is this here -1? So here it's obvious, 0 and 2, right? But here, of course, you have, okay, yeah. So here you have, okay, yeah. This is why it's not, maybe I can draw on this. Can I draw on this? Or I can just copy this. And, can I make copy? I guess I could make a PDF annotation. Do I have a PDF No, it's just a reader. I don't have full program here, right?
You can screenshot the...
Yeah, that's what I'm gonna do. I'm gonna do that again. Windows print screen, right? Good old friend, right? Then we have our paint friend. Control new paint, and we have Control V. Control V. Come on. Sorry. I'll do it one more time. Shift. I think Shift Windows print screen. I think was. Oh no, function key. Sorry, also function key. Right.
Shift Windows key S.
Yeah. Yeah. There you go. All right. Let's crop. There you go. On Control Y, I believe it was, right? Crop, yeah? Yeah, all right. Now I can go and do my drawing with my pen. Right, so idea is this is -1, basically. Right, oops. That's what I was thinking about. -1, so that's the problem, right? That's where this -1 came from, basically, right? Because there's nothing. So that's why I like the one visualization use 0, right? Here, there's -1. So that's where this balance is, right? So if it does not exist, right, it's so here it's also -1, right? You know, -1, but this is fine. This is fine. Fine. This is not fine, right? So this is the bad, right? Yeah. So this one here, right? Was this -1, -1? Okay. 0, 1, right? So again, you have -1, -1, right? And again, different literature. That's the problem is literature, right? Sometimes, you know, scientists or researchers, they decide to use slightly different notation, and then you see, okay, if you're comparing two papers or doing some research, and you say, okay, why is this? What notation is being used, right? So that's something that makes things a little bit harder than it should be, maybe. Okay, but now you see why this is bad. Bad, right? Right. Here it's obvious. No, it's no. You see also bad. Or maybe you see -2 is not so bad. In, you know, red black trees are low -2, right? AVL trees are stricter. Okay. Now, so how do we fix this? Well, rotations, right? Let's keep going. We have some how many slides do we have? Oh, quite a few. Okay, right. So if you look at these, a good insertion case, right? So middle, tall and small. Okay, right. So a good case, insert the first, right? So this is completely fine, right? Insert middle first, then small and tall, and this is nothing changes, right? Like you enter 3 numbers. On this case, insert small, middle, you know, this breaks, right? So we started with the smallest, the middle, and then the tallest, right? So the solution is, of course, this will rotate up, right? And small goes down, right? Easy, right? This one, we know how to solve this. Of course, one thing is solving it in theory, you know, with pen and paper, but actually writing this code in some language, right? That's involved, and so that's why that's easy to make it go wrong, because of course the implementation will involve some sort of tree-like structure, pointers most likely, right? And if you do it in incorrect order, things will be painful. All right, so this is one. We'll show this. Yeah, so single rotation, right? So this is how you fix it, right? So a right child could legally have its parent as its left child, right? So a right child, right? This one here, SM, right? M becomes the parent, S becomes the left child. Everyone makes sense to everyone? Okay, excellent. Now, to the general case, let's see here, high plus 1, high plus 2, right? So where do we have a problem here? Here's the problem. Do you mean?
H plus 1 and H.
Yeah, this is the problem here, right? So I guess this, gained extra height, I guess, right? Gain extra height, right? Left, right? So how do we solve it? We'll have to move up, right? Yeah. Moves up, B moves up, becomes the new root, A moves down, but look at this here, this is the tricky part, right? See? We can do this type of rotation, look at this. But A, the previous root, takes on the child from the new root, basically, right? Because there's no space. It's all full basically, right? You need to move it. And now h minus 1, h minus 1, right? So now everything looks pretty decent, right? So this is a good way, fixes the case one imbalance. Tricky, right? That's it. You can stop here. So let's look at this one, right? So this is a different, small, tall, middle, right? Still not good, right? So left, right, left, right, left. So can we fix the single rotation? Single rotation won't fix, so how should it look like, right? What should it look like? It should look like middle should be, yeah, on a, yeah. So M, top and S to the left of M, right? That would be good. So this is, I guess they call it double rotation, right? I believe it's going double. Let's check. Indeed. So they call it double rotation, right? So middle goes to the, well, middle, and yeah. So yeah, okay. So that's why it's called double rotation. So because we regress, we reduce to the single case, right? We saw this already a couple slides back, right? We saw it here, right? Yeah, we saw this, right? So here we do this rotation to get this. So rotation means, I guess, swapping the two elements. I guess that's why I call it rotation, right? And then finally we have it here, right? And then we rotate back. So we know how to solve this. So this is like the harder case. Okay, but now if you get this in general bad case, well, let's leave this up for a moment, maybe if this makes sense. So we move, so this is allowed, right? We change them, and then we have it. Everyone? Makes sense?
Yes.
Okay. How about everyone else? More or less? More or less. Okay. So now this is the bad case. So left, right imbalance. So idea is this, that it's left imbalance and then right imbalance. So here's the imbalance, right? You see the imbalance here, right? We need to fix it, right? So this will be a double rotation. Double rotation. So this is gonna hurt you. Yeah, like I said, h plus 1. So we move, and I don't know if these slides are so great actually, because it's kind of hard to follow, right? Let's see this. This is where we started, right? Yeah. Added something here, right? This is the new imbalance, right? Everything was fine before. Now we need to move it. Need to move it, right? So xy on A and B, C, right? A, B, yeah, okay, A, B, C. So at end of the day, C moves up, right? On whatever children it had. So left side children go live with the B. On the right side children of C, right, go live with the A, right? Because we now, if you think of it, makes sense, right? Because when we're moving up, B B has empty space here, so we can give it the left side children of C, and it will still match the binary search condition. And C doesn't need any children because it has new children, right? B and A, right? On A, the old root, right? It doesn't have left side. So we can attach anything that is here. So again, only two rotations. It looks really ugly, right? To me. But it is actually not so, two rotations basically. So that's the algorithm. Find spot for value, hang new node, and you search back for imbalances, right? So there can be only one imbalance. That's amazing actually. So that's kind of cool actually, right? Single rotation, double rotation, and that's it.
But what was the case for identifying the double case?
Okay, the difference is because so basically how left right basically you have two cases. Like, okay, let me paint it. Let me paint again. Right, we get painters. Yeah. So we have two imbalances. We have.
Well, I understand
Yeah.
the idea of small, tall, middle,
Yeah.
but how do you identify them?
You have pointers, right? You have pointers left, right. Everybody has left, right. You check, right? So you see right, where the imbalance is, right? You can check by pointers, right? But you have two properties. Each node has a property, right? Left, right. And you can check whether it's left, right, where the imbalance lies, right? So whether it goes, because you remember, you're probably going to implement this as double E link. You know, here's the links, right, both ways, right? Because you want to go back and forth, right? You want to easily travel back and forth, right? So you can check where the problem is, basically, right? And then you can reduce this case. So basically, you have a left, right, 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 left, or left, left, and right, right. So these are single rotations. Single rotation, single rotation. You know, right? You know, left, left, right, right, right? And these are the ones, so left, right, and right, double rotations, two rotations, right? And that's all the case we have, where we have, basically we have to figure out that the imbalance can only occur at one place, basically. As long as it's still, if it was previously AVL3, of course, right? If it was not AVL3, then we have a problem, right? So, maybe when we do it, we'll do it a break. We'll see if let's check our C++ code. See if we can actually see how it's done. Actually, maybe it'll make more clear, right? But so your question is, how do you determine which case it is, right?
Yeah, because why not in the left, right, right, left case, not just rotate?
Yeah, but here you can't. I mean, we know it's double rotation basically. It's double rotation, right? So, so you are proposing a single rotation here, and maybe.
I think I want to see more examples of both of these cases.
Okay. All right. Let's continue at 12:10. Is that okay? Right. Okay. Okay.